Hi everyone, my name is Max Weiherer and I'm presenting our paper Approximating Intersections and Differences between Linear Statistical Shape Models using Markov chain Monte Carlo. Traditionally, the comparison of statistical shape models is mostly performance-based, carried out by applying metrics such as compactness, generalization, and specificity, or by evaluating the model on downstream applications such as shape prediction or classification. To date, a visual inspection of similarities or differences between actual shape spaces is not possible. A visualization can only be provided for the individual shape spaces by inspecting random samples or the first principal modes of variations. With this work, we present a new approach that allows for a qualitative and direct comparison of two linear shape models and dense correspondence. Specifically, we propose to compute intersections and set-theoretic differences between the model shape spaces to study similarities and differences between SSMs built from different populations. Our method has several interesting applications beyond just data exploration. For instance, the proposed algorithm may be used to study demographic bias in statistical shape models, or it could be utilized to visualize similarities and differences between healthy and pathological models of human bones or organs. It may also support product designer when developing new products or adapting existing ones for a specific market. In summary, the key contributions of our paper are: we present a new method that enables qualitative comparison of two SSMs by computing approximate intersection spaces and set-theoretic differences between their low-dimensional allowable shape domains. We provide an extensive quantitative evaluation based on synthetic and real-world data. And lastly, we analyze similarities and differences between face models, including the Basel face model, Flame, and the Liverpool-York-Cat model in terms of gender-specific male and female and identity and expression shape variation. To start with, recall that a linear, PCA-based shape model, also known as point distribution model, can be represented as a function mapping low-dimensional parameters, alpha, to 3D shapes discretized using endpoints in space. Since our model is generative, we can easily synthesize new shape instances by varying alpha. The vector space spanned by the model is an affine, q-dimensional subspace of the 3 times n-dimensional space and contains all shapes that can be represented by the model. If we further assume that the model parameters alpha follow a zero-mean normal distribution, we observe that shapes x are also normally distributed. From this perspective, not every shape in the vector space M is equally likely. The probability mass is concentrated in a q-dimensional hyper-ellipsoid, which is centered at the mean and whose principal axes correspond to the eigenvectors of the covariance matrix C. This hyper-ellipsoid Q is known as the allowable shape domain and contains only plausible shapes. In this work, we define the intersection between two SSMs and dense correspondence as the intersection between their allowable shape domains. As seen, a shape X belongs to the intersection if and only if it can be represented in both models and if it's also likely in both models. Due to noise contained in real-world models, however, we cannot compute the exact intersection space, but instead formulate an approximate intersection, allowing us to also consider shapes that are almost up to an epsilon contained in the true intersection. To actually compute the intersection, we propose to estimate the distribution of shapes lying in that space instead of an explicit construction using rejection sampling. In detail, we propose to model the distribution of points x in Q1 given that x belongs to the intersection space. To do so, we employ a product of the following two likelihoods. A distance likelihood that it used to ensure that x can be represented in both models. We evaluate whether a point x sampled from Q1 can be represented in the second model by computing its closest point contained in M2, given by the orthogonal projection. And second, a projection likelihood used to ensure that x is likely in both models. Finally, we use Markov chain Monte Carlo and the Metropolis-Hastings algorithm to approximate the intractable posterior distribution and, based on the posterior samples, compute a basis for the intersection space. We can easily adapt our algorithm to also compute set-theoretic differences between two SSMs. Specifically, we define the difference between two models as the set containing all shapes that can be represented and are likely in one model but not the other. This is implemented by simply inverting the distance likelihood. Since we no longer require x to be likely in both models, we simply remove the projection likelihood. It's important to note that the set-theoretic difference doesn't lead to a convex space. Indeed, the space we're ending up with is non-convex. As such, it doesn't make any sense to apply PCA to the posterior samples, which is why we only visualize random samples drawn from our Markov chain in order to inspect the difference. We provide an extensive quantitative evaluation in terms of synthetic and real-world dataset. For the synthetic dataset, we use a 5-pointed star as a simple geometric object to generate training data by systematically varying its points. Note that this also provides us ground truth intersection spaces as well as samples from the ground truth difference between two models. We tested our method on various configurations and measured an average Grassmann distance of 0.01 between estimated intersection and ground truth, leading to the conclusion that we are able to recover ground truth intersection spaces accurately. To evaluate estimated differences, we report reconstruction errors of posterior samples projected into the ground truth intersection space. We observe similar results as for intersections, which is also supported by the provided visualization of the posterior sample distribution. For the real dataset, we randomly split a set of basis vectors of a real SSM into 3 sets as shown. However, while this provides us ground truth intersection spaces, we note that for real-world SSMs, it's generally not possible to construct ground truth differences and samples thereof. The following table presents computed Grassmann distances with an average distance of 0.1. Interestingly, we observe increasing distances as the dimension of the intersection increases. This is because MCMC doesn't properly sample the entire space. By doubling the number of chains, however, we could lower the Grassmann distance by more than 10%. To showcase our method on real-world SSMs, we compute and analyze intersections and differences between gender-specific male and female models of the Liverpool York Head model and Flame. As seen, random faces sampled from the intersection model do not show a strong preference towards male or female, and most of the time tend to look more neutral compared to faces drawn from the individual male and female models. Furthermore, while random faces from the difference between male and female show extremely masculine traits, samples from the difference between female and male look rather feminine. We observe similar results for Flame. We further analyze intersection spaces and differences between identity and expression models of the Basel face model and Flame. Here, we also demonstrate that our method is able to highlight similarities and differences on a per-vertex level, which is achieved by plotting the per-vertex posterior variance. As seen, shape variations of the nose and cheeks are unique to the identity model. While the opening of the mouth and rising eyebrows is solely represented in the expression space. For Flame, neck and ears are uniquely represented in the identity model. And movement of the mouth is solely represented in the expression model. To summarize, we have introduced a new method to compare two SSMs by computing approximate intersection spaces and set-theoretic differences between their allowable shape domains. We showed how MCMC can be leveraged to approximate the distribution of shapes lying inside those spaces. Based on our quantitative evaluation on synthetic and real-world data, we found that the proposed method is able to recover ground truth intersection spaces and differences accurately, and the presented qualitative results on popular face models match our intuition.